All right, welcome back everybody. So today we'll be looking at the problem min costs of climbing stairs. So let's read the problem. On a staircase, the ith step has some non-negative cost, the cost of I assigned 0 index. Once you pay the cost, you can either climb 1 or 2 steps. You need to find minimum cost to reach the top of the floor, and you can either start from the step with index 0 or the step with index 1. So let's look at the first example. It says cost, and we have a list of 10, 15, and 20. And so the cheapest cost, or the minimum cost that we can pay to climb the stair, is 15. And it's important to understand why. So if we look at this, remember the problem says we can start at either index 0 or 1, so the first or second index, and then we can move 1 or 2 spaces. So if we start at 10, we can either move to 15 or 20. If that's the case, then we'll incur a cost of 25 or 30. But if we start at the second index at 15, we can either move to 20, which will incur a cost of 35, or we can just skip past that and move 2, which if that's the case, we've reached the end, and then we can just return 15 because that was the only number that we had. Then another example below, you can see a cost of 1, 100, 111, 100, 11, 100, 1. And so the minimum cost here is 6 because at any point in time, we either have a 1 or 100, and so obviously 1 is less than 100, so we're going to go with that pretty much every single time. But yeah, you can just sort of eyeball example 2 and sort of guess as to how we got that answer, or sort of reason as to how we got that answer. So if we start at 1, then we move 2, we end up with a 1, and then a 1 and a 1, and so on and so forth. So at any point, it's important to understand that you can move 1 or 2 steps, and you can start from the first or second index. So that needs to be taken into account. And so with that being said, let's go and draw this problem out so we can get a better understanding of it. All right, so let's start with an input. So I'll just take the input from the second example we saw. Okay, so remember with our problem, we can start either 0 index or the first index, so the first and second index respectively. And so from here, from 1, we can either look here or here. And then from here, we can look here or here. And so essentially this can repeat through the entire list. And at every step, we're essentially just choosing the minimum cost. So obviously, if it's between 1 and 100, again, it's just going to be 1. And so we can calculate that as we go through to get our final answer of 6. Now you may be thinking to yourself, how can I efficiently do this? Because if you look right here, at any given point in time, you can either move 1 or 2 steps. And so because of all these choices, it seems like there is possibly some recursion involved, because you could very easily select the starting point and then recurse by moving either 1 or 2 spaces ahead. And you can do that until you reach the end, at which case then you'll calculate your answer by selecting the minimum cost. Now, this works, but it's not really ideal because you're incurring exponential time space, or you're incurring an exponential runtime because of recursion. Because when you recurse, you put that function call on a stack, and it's not guaranteed, or at some point you're probably going to repeat work, and so that adds up and doesn't give an efficient runtime. So with this problem, I like this because for most candidates, they struggle with a concept called dynamic programming, and a min cost of climbing stairs is sort of an easy introductory problem to sort of understanding how we can take a recursive solution and make it more dynamic, or improve it with dynamic programming. So how can we do that? Well, the first step that I can think of is we can create an extra list. So the list will be similar to the length of the input list that we have, and it'll be filled with zeros, and then from there we can use existing data to build up our answer. So what do I mean by this? Well, first let's start off by declaring an auxiliary list, right? And so this, I'll actually make it the cost, or the length of our input array, so it'll be called cost, plus 1. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it'll be of size 11. So let me just get that out. Just imagine this whole list is filled with zeros. So it's just a list of zeros of size length of our input plus 1. And so the zeros are just a placeholder. We're not going to leave them as none. So we're just going to put a default value in there, which will be 0. And essentially all we're doing is we're going to set the initial values within our list. So the first two values, right? Because remember, we can start either the first or second index. And so we can take the values right here from our inputs and put them right here, right? And so this right here is enough for us to build up our build up our answer just from these two values. So we can set these in the initial two spots, and then we can actually start in the third index, because when we start the third index, we would have had to have made a choice between moving one or two spaces before, right here, right? And so it makes sense in this scenario because we have the two starting points can take place in 0 and 1 index respectively. So if we start at the the third index, if that's our starting points, then we know by that point we would have had to have made a choice already. And the choice is pretty clear at this point. We're finding the minimum costs between those two choices. And so all we can do here is, as long as we haven't reached the end, we can take this value, so the value at the third index, plus the smallest number, so in this case 1, so we'll get 2, right? And then we come here to the fourth index, and so what is smaller, 2 or 10, or 2 or 100? Well, obviously 2, so it'd be 1 plus 2, so we get 3. Move here. What's smaller, 2 or 3? Well, 2 plus 1, so we still get 3. Come here again, 100. What's smaller, 100 or 3? Or sorry, 3 or 3? Well, all we get is 3, so it'd be 3 plus 100, so we get 103. Okay, so now we're at 1 again. So what's smaller, 3 or 103? 3. So 3 plus 4, so 3 plus 1 is 4. Come here, 1. So what's smaller, 4 or 103? 4. So 4 plus 1, 5. Okay, at 100. And then we come here to 100. So 100, we look at the two previous, so 5 and 5. Well, 5 is the smallest here, so we're just going to put 105, because 5 plus 100. Then we reach our ends. Then we have 1. So what's smaller, 5 or 105? Obviously 5, so 5 plus 1 gives us a total of 6. And then we reach our end. So all we have to do is we just return. So remember we'll just call this auxiliary list, DP, just short for dynamic programming. We can just return -1. So in Python, this is just saying return the last element right here. And so this is our answer. This is congruent with the output of the second example from the LeetCode problem. And that's pretty much it. So this is classic dynamic programming. You essentially start with little data, and you use that little data to build up eventually to get our final answer. And so the runtime of this is, since we're only doing this in one pass, it's O of n, and then the space is also O of n, because we have to create, an auxiliary array the size of our input array. So because of that, it's also O of n. Now, without confusing you guys too much, there is another way to improve upon this. So with most dynamic programming, you will create essentially an empty copy of the input and then build your answer up from that. But if you really want to get more efficient, you can actually do away with that copy entirely and actually just build up the answer with two values. So remember in the beginning how we started with the first two values here filled out. Well, that's really all we need. We actually don't need the entire list right here. If we can just get access to the two previous values, then we can just incrementally, build up our answer that way. So we actually don't need the entire list. And so if we can get away or do away with the entire auxiliary list, then the space will go down to O of 1. So that's just a little improvement I want to mention here. But in the final code implementation, I'll just do it the first way that we covered here. Because I still think it's important to learn how to do it the first way, because building up your answers with an auxiliary list is a very common dynamic programming concept. And so in an interview, you still want to show that. I mean, of course, you could improve upon it to really impress the interviewer, but at a base level, I think the first way is probably the way you want to begin by doing it. Okay, so hopefully that makes sense. So yeah, now we're going to go look at the code. So first things first, when you're dealing with any problem, you want to think of edge cases. So what's the edge case here? Well, the simplest one is if the cost input is empty, then we just return 0, right? So that's just a little cursory check we can do. Now what we want to do is with this approach in dynamic programming, you always want to start by creating a separate auxiliary data structure. So in this case, since we have a list, we'll create an auxiliary list. The size of our inputs plus 1. So what that look like is we'll just say dp equals 0. So that'll be the default value within our list times length of cost plus 1. And so the reason why we want to add plus 1 is just because there's a little bit of buffer at the end that'll allow us to look at the last previous numbers and then calculate the solution that way. And so when we reach the end, we also want to make sure that we aren't adding, since it's plus 1, so it's beyond the bounds of our input cost. So because of that, we won't be adding the value at that index because it doesn't exist. So when we reach the end, we want to make sure that we add 0 plus the last two, or the smallest of the two previous numbers. So that's why we add this plus 1 buffer right here. So hopefully that makes sense. And so what we do here is if length of cost is less than 2, so another edge case here, if it's empty, we do one thing, but if it's less than 2, then all we can do at this point is just return costs 1. Just remember, edge cases are important. So now what we want to do here is set the initial value. So currently the DP list is all zeros. So what we want to do is set the first two values. So we get that from our input cost. So essentially we can just do this, DP 0, so the first index, and DP second index equals cost 0, cost 1. So that'll set us up with our initial data from which we can build our answer upon. So now we can enter a for loop, so for x in range. So remember, because we have these two values at the 0 and 1 index, we'll have to start at the second index. So 2 to the length cost plus 1. And so a lot of people find dynamic programming pretty intimidating, but once you kind of get the process down, it's really simple. Like the logic for this code in the for loop is really just one line, and then that's pretty much it. It does everything we need it to do. So what we want to do is say dpx, so the location in our auxiliary list will be set to the minimum of dp x minus 1, so the previous value, or value before our previous value. So that would just be x minus 2, right? And then we want to add a final clause here. So remember in the beginning I mentioned if we reach the very end, if we reach the buffer area right here, we can't access the value at that index because it doesn't exist. So we will add 0 to the calculation. So 0 if x is equal to length cost. Else, then we just return the value at that index. And that's pretty much it. So as you can see, if you cross-reference this with the picture I drew in the previous section, we start the second index and we look at the previous two values, get the minimum, and then we just add the cost. Once we reach the end, we just add 0 to it, so it'll just be the smallest between these two, and then all we have to do at this point is we just return dp minus 1. So we just return the final value that we've calculated in this list, because this list, the whole goal of it is just to build up our answer, and then the very last value is guaranteed to be the result that we're looking for, because it just essentially cumulatively builds up as we go through the list. So that being said, everything looks good here. Let me just do one last look. So, okay, we have our edge case. We've constructed our lists, another edge case, set our values, iterated. Yeah, everything's looking good. So I'm going to go ahead and run this and see what we get. Okay, so it passes the initial case. Let's submit this. All right, perfect. And it's 90% faster than other submissions, so that's pretty good too. So this is pretty much how most dynamic programming problems work. Just remember that dynamic programming, you have to identify that recursion, or that there's overlapping subproblems. So that's essentially recursion, because recursion inherently does duplicate work. And then when you identify that, then you can improve upon it. The simplest way to do that is by creating an auxiliary data structure and then using initial values given to you. So in the case of this problem, it's just dealing with the last two values. And then we can use that to build up our information within our auxiliary list, so we can ultimately return the last value. Like I said, this is a common pattern in a lot of dynamic programming problems, so I really encourage you to really understand and dive deep into how this works. So yeah, that's going to do it for this one, and I'll see you guys in the next one.